This is Dr. Shiella Tikku speaking for class 3rd year. The topic is magnetic properties. 5. Quenching of orbital contribution. The quenching of orbital contribution is the contribution for an electron to have orbital angular moment which it does on the axis as well as it does on the orbit. We have the shape of d orbital showing their orientation to each other. An electron of these orbitals has orbital angular momentum, that is dz square. Electron, on the other hand, does not has angular momentum about z-axis. In an octahedral or octahedral complex, the dz and yz orbitals are rotationally equivalent, but dxy and dz square dash y square orbital do not separate by delta a and dz square. The contribution of dxy and dx square dash y square is not completely quenched by ligand field. In an octahedral field, the total momentum is quenched with the ground state configuration, that is T2G and T2G3 or T2G6, which are commonly high spin complexes. Consideration of octahedral species is the case in which such orbitals are not taken into consideration. The orbitals which are taken into consideration are mainly in which octahedral complex has the widest contribution. In cobalt 2 complex, the octahedral complex is formed when one electron jumps into the 4d orbital because it is d7 system. We have mu e is equal to mu spin and lambda is equal to 170 centimeter inverse. Applications of magnetic moment data for 3D orbitals. Mu effective is equivalent to under root n into n plus 2. The quantity of The name implies derived by assuming the angular momentum. For example, find the oxidation state of iron, a complex FeL6N+, its geometry and nature of ligand with the help of the magnetic moment value, where mu is equal to 5.9. Now we know that when mu is 5.9, that means the number of unpaired electrons will be more. So we can calculate mu by under root n into n plus 2. 5.9 is equal to under root n into n plus 2. Then n square plus 2n is equivalent to 34.81. Then we have n square plus 2n minus 34.81 is equal to 0. The quadratic equation of this calculates and the number of electrons come out to be 5. According to this, iron is in the state of +3 oxidation state, which has 3d5, 4s0 and 4p again 0. Then we have iron, which this type of compound is a high spin complex, and in this type of high spin complex all the electrons are unpaired. The electrons first go to the T2G level and then they go to the EG level. The difference in between the two is lambda O. Second example is chromium. The geometry of chromium and following magnetic movement. According to this, we have the oxidation state of chromium +6, in which all the electrons are unpaired. We have chromium in the oxidation state of +7, and in this state we have the hybridization of D2sp3. This D2sp3 hybridization is possible when the electrons shift down. When the electrons in chromium are paired, and when such type of state occurs, the compound is low spin complex and the hybridization is D2sp3. This low spin complex has 2 orbitals empty because the paired electrons enter into the T2G orbital and the EG orbital is empty.